Hello and welcome. My name is Hugo Currie and I'm a Year 12 high school student at the Riverina Anglican College in Wagga Wagga, Australia. This is a series of brief interviews with some of the most amazing physicists from around the world. I'm passionate about physics and will pursue a career in physics and engineering, so I'm honoured to be able to ask a few questions of some inspirational physicists. I really want to thank them all for generously taking the time to chat and, importantly, passing on their rich insights. Hopefully other students with an aptitude for physics can take inspiration and guidance from experience and insights to shape the next generation of physicists. Today I'm speaking to Professor Steve Meikle. Professor Meikle is a Professor of Medical Imaging Physics at the University of Sydney, Head of Imaging Physics at the Brain and Mind Research Institute, and Research Academic Director in the Faculty of Medicine and Health at the University of Sydney. He is a Fellow of the Australian Institute of Physics, a Senior Member of the IEEE, and an Honorary Professorial Fellow at the Centre for Medical Radiation Physics at the University of Wollongong. He is also the President of the IEEE Nuclear and Plasma Sciences Society. Professor Meikle is internationally recognised for his expertise in imaging physics and quantitative approaches, and specifically in advanced imaging methods to quantitatively evaluate molecular mechanisms regulating brain function. Thanks, Steve, for taking the time to share your thoughts and experiences.
It's my pleasure, Hugo.
So firstly, I'm interested to know what drew you to a career in physics and I guess what excites you about it.
Yeah, so I think there's a couple of things, but more than being attracted to physics, I think it's really the combination of physics with medicine and biology. When I was at high school, I really enjoyed all the branches of science, but I think I was actually more drawn to biology than I was to physics at the time. But I had no idea back then that it was possible to combine those, particularly those two branches. I thought of them as sort of distinct branches of science. But then I got into nuclear medicine, and that came about really because I wasn't exactly sure what I wanted to do after I left high school. I didn't think I was ready to go to university, and I wasn't sure what I wanted to do. And it so happened I had a relative who worked in nuclear medicine who told me about it, and so I thought, well, at that time, you didn't have to go away to university to study first before you got into nuclear medicine. So I could go straight into a traineeship and learn about the field. And I really enjoyed it. I enjoyed that contact with patients, but using technology to help them. And that's really when I first saw how you could combine physics with medicine and later on with more fundamental biology. So I think it's that combination that I really enjoyed, and I really also got excited by the possibility that you could develop some physics approaches and solutions and see them implemented and make a difference really quite quickly. You could almost, as particularly in the early days of nuclear medicine, you could develop a new technique and then implement it in the hospital in routine clinical practice rather quickly and see that it actually makes a difference. So that's what I really enjoy about the field and what got me excited in the early days.
Yeah, that's I agree. I like physics, especially it's being applicable to all the other different fields, I guess. So even in the subjects that I'm doing, such as geography, we're learning about river systems and physics there and whatnot. So I really enjoy being able to relate it to everything else.
Yeah, that's right. And physics is such a broad field, as are the other fundamental sciences. So you can same as chemistry and mathematics, you can apply physics to just about any branch of application you like to think of that affects us every day. So I happen to really enjoy that combination with health and medicine, but you can apply it just as as well to the environment, to technology, to climate change, to all sorts of other areas.
Yeah, so talking about that, what would you see? What do you think you see on the horizon, I guess, that would inspire the next generation of physicists?
Well, I think broadly speaking, so not just thinking about my own field, I think the really nice thing about physics is that you can apply it, use all the skills you develop in physics, and apply it to some of the biggest problems that are facing us. So, you know, as I already mentioned, climate change. You can think about, you know, the next generation is going to have to deal with a really quite rapid transition in the way we harness energy towards renewable energy. And so there's going to be, I think, a real need for physicists and engineers and mathematicians to find to develop new technologies that are going to make that transition feasible and scalable and economic. And similarly, yeah, climate change. I think also in my own field, I think there's still a long way to go in terms of developing technology that can really solve some of the bigger problems in health, like long-term disability and chronic diseases that have such a big impact on people's lives. I think we're really only just starting to scratch the surface of what's possible with the technologies we have now, and I think we're going to need new technologies in the future to really address some of those big problems.
Yeah. So, in your field specifically, the other week when you chatted to our physics cohort, I really enjoyed the part talking about being able to scan moving animals, I guess. I thought that was really interesting. And so I guess, do you see that technology or similar things that are, I guess, do you see the way that scanning and that sort of thing is done? Do you see that changing, or do you see other things changing around it, I guess?
Yeah. So I think when we tried to solve that problem, it seemed like a really tough problem to solve, and I think they're often the most fun problems, right? Because you've really got to get creative if you're going to solve these sorts of problems. So just to perhaps to explain for the audience, for those who didn't hear our conversation the other day. So this is about applying the same sorts of imaging techniques as we use in clinical practice, and specifically PET, where we use radiopharmaceuticals and take images of the radiopharmaceutical distribution in the body to measure biological function, and that's we use that very routinely in different types of human diseases. But we also use it to image small animals that can act as models of human disease. But the big problem, of course, is that animals move unless you anesthetize them. But if you anesthetize them, that affects their brain function. So it affects the very things that we're trying to observe through our imaging techniques. So we were trying to come up to a solution to that problem. So we developed a range of different technological approaches, some motion tracking, some maths and some algorithmic solutions that correct for that motion, and also a bit of robotics along the way. And so combining all those solutions allowed us to take these PET images of animals when they're awake and moving around, and that opens up a whole lot of possibilities to study not only brain function but also the behavior of these animals, and you can do some very interesting things scientifically with that. And so to come to your question, yeah, look, I think that the techniques we use, the solutions we came up with, are still rather crude, actually. They work, and we demonstrated that, that this can be done, but they're still quite crude solutions. And so, yeah, I think there's enormous scope to develop newer and better technologies to make that work much better than it does at the moment in the future. And I think there's also a huge opportunity to translate those methods to human imaging. So with human imaging, even though we can tell the patient to lie still most of the time, and they do, there are patients who either don't understand the instructions, or they're uncooperative for whatever reason. It could be because they have a dementia or some kind of disability or behavioural problem, or it could be because it's a young child. And so there's still situations in medical imaging, in routine clinical practice, where we can't keep the patient still, and we need to be able to measure and correct for the motion. And it's still a big problem in medical imaging. So I think there's a lot of opportunity for us to solve those problems in clinical practice, as well as in research applications of PET.
Yeah, that sounds really interesting. Yeah. So you mentioned before, in developing that system, there was a wide range of things that were required to solve the problem, such as robotics and physics and programming and algorithms, that sort of thing. I'm interested to know what skills you've relied on most throughout your career, I guess, as medical physicist. Sorry.
Yeah. Okay. So I think there's a number of skills that are important in medical physics and in many other fields as well. But I think first and foremost, problem solving, just having the skills and the perseverance to solve tough problems, and that brings me to one of the other skills you need. So when you're trying to solve a very challenging problem, most of the time you can't do it on your own. You need to do it with a team of people, and so you need to be able to collaborate. You need to be able to identify and find the people that have the skills that you don't have, so that you can work together to solve these problems. And that means you also need some team building skills. You need the ability to motivate a group of people with complementary skills to all work on a problem together. And when you do that, you find you can make incredible progress in quite a short period of time. So I think those skills are really important. And I think the other thing that's important is communication skills. I guess you need good communication skills to build that team and make sure the team works well together, but also to explain your research to other people, to other researchers in your field and clinicians and practitioners, so that they understand what you're trying to do and how you've solved the problem. But also to the public, we need to be able to communicate how we're using public funds to do research and to develop technology that's going to help society. So I think all of those things are very important.
Yeah, definitely. I think it's good to teamwork is so important, and communication, I think, is a common theme through a bunch of the range of people that I've talked to. Everyone is very seems to think that communication is very important for a future in or doing well in a subject, I guess.
Yeah, I think it definitely is, and I think the days when you could kind of just work on your own to solve a problem, and you could just write up your results in a journal and then move on to the next problem. I think those days are gone. I think the sorts of problems we need to solve really do need multidisciplinary skills and really good communication skills. I think the other reason that communication is important is we need to be able to explain to the funders of our research why our research is important, And it's getting very, very competitive and very tough to get research funds from almost from any source, really. And so you need to be able to communicate very clearly why your research is important and what impact it's going to have on society to have a chance of securing funds. So there's lots of reasons communication is really important.
Yeah, definitely. So to briefly talk about PET, I was chatting the other day about quantum computing, and someone suggested that the two 511 keV gamma rays from the positron's annihilation are entangled, and that quantum physics might have a role or be able to re-engineer PET imaging as a whole. I'm interested to know whether you've got any thoughts about that.
Yeah, well, that's very true, and it's something that's only relatively recently been discussed. It's been known for a long time that there's quantum entanglement that between those two annihilation photons, as you mentioned, but we've never exploited that. We just treat the two gamma rays as if they're completely uncorrelated, except in time, right? But there is quantum entanglement, and there's some characteristics of that we could potentially exploit if we had the right technology. And we're not there yet. It's going to require different types of detectors than the ones we have now. But I think if that technology can be developed, then there is the possibility to extract additional information from the detection of the pair of annihilation gamma rays that could help us with improved, for example, improved scatter correction, and also it could be that we could, there's other information there that could be exploited to improve the quality of the images that we create. So it's not an area I'm actively working on. I have some colleagues that have done a lot of theoretical and modeling work in this space. But I think it's an area that I think people will continue to work on it. And I think eventually the technology will catch up with the idea for sure.
Yeah, cool. Yeah, it is a very interesting topic, I think. Yeah.
Mm.
So you've had such an amazing career. I'm interested to know what you consider to be the highlight, I guess.
Oh, look, there's been a few highlights. They tend to be, sometimes they're a long way apart in a long career. But look, I'd say one of the earliest highlights for me personally was some of the work I did during my PhD when at the time, the way we were doing whole body PET images, we were not doing attenuation correction routinely. And so the images had a lot of artifacts. They were also very noisy images. They didn't look anything like the PET images that we see today. And so I did some work that tried to address both of those problems. We developed a method that enabled us to do routine attenuation correction on clinical whole body scans. And also there was a very new method of image reconstruction, a statistical method that was developed in Sydney. It wasn't something that I worked on directly, but my colleagues at Royal Prince Alfred, Brian Hutton and his colleagues at Macquarie University, Malcolm Hudson and Rick Larkin, developed an algorithm called OSEM. And everybody in our field knows that algorithm very well, of course, now, because it's used routinely in every hospital and nuclear medicine department. But at the time I was doing my PhD, nobody had heard of it. Nobody was using it. And I realized that it could play a role with these noisy whole body images. And so when I combined those things and saw how much they improved the quality of our whole body PET images, and it was a little like I was saying earlier on, having developed these techniques, we were able to put them into routine clinical practice almost immediately, and the quality of our clinical images improved overnight. Though it was a dramatic improvement. So for a while there, we were producing by far the best whole body PET images in the world, and you know, they made a really big difference to the clinical outcome for the patients who had those scans. It didn't take very long before all those methods were superseded, and about, I guess, less than 10 years later, PET-CT was developed, and that superseded some of the methods we developed, but not OSEM. OSEM has remained the gold standard in PET, and so yeah, I'm very, very proud of that work and that achievement. We talked about the small animal imaging. I think that was a highlight for a different reason, because I saw how we could develop techniques which could be applied in fairly fundamental, not basic research, it's still applied research, but to a very fundamental area of neuroscience. And so now we're collaborating with psychologists and neuroscientists at the University of New South Wales who are using our awake animal imaging technique to look into the role of a specific chemical in the brain, a neurotransmitter called dopamine, and how it regulates behavior and learning, and how dopamine causes the brain to adapt to new situations and learn from those new situations, and then grow new neurons, so the plasticity of the brain. So it's a fairly exciting area of neuroscience to be involved in, and that's been a highlight as well. I guess the other thing is just seeing what some of my graduates have gone on to do. So I've had the good fortune to supervise a number of really smart PhD students who've graduated and gone on to do all sorts of amazing things themselves, both in industry and in academia and in clinical practice. So that's very, very rewarding as well.
Yeah, I can imagine. Yeah. So, is there anything in physics that's important or contentious that you'd like to see the next generation of physicists work on?
Yeah, look, I guess there's always things where you're pushing the technological boundaries where they're potentially contentious, but have or high risk, but have potentially very high reward. And I mean, one area that comes to mind that's outside of my field, but I think is fascinating and has the potential to make a really huge difference to people's lives, is this idea of computer brain interface, or in the case of the work I'm thinking of in particular, it was really interfacing the spine with smart devices in order to overcome the disability that comes from traumatic spinal injury. So in that area, what people are trying to do is develop very small devices, smart devices, that you can implant in the body, either in the brain or, in this case, above and below the spinal injury, that can receive sensory information from the world around us, process that data, and transmit that to another device wirelessly below the spinal injury, that can turn those signals into movements, and so recover some of the lost function that people have when they have a traumatic spinal injury. And some of the results I've seen coming out of Stanford in that area just recently are just so impressive. And it makes me think that it won't be too long before that technology is evolved sufficiently that it could be it could really make a massive difference to the lives of people that have spinal injuries. And I think just thinking about a related area in terms of computer brain interfaces, I think there's a lot of possibilities there as well. But where the contentious part comes in, I think, is I think there's been a lot of progress in developing devices that can be implanted in the brain, or as I said, in the spine, and they can do a lot of very sophisticated signal processing at the individual neuron level or clusters of neurons in the brain. But the contentious part is, I think, where artificial intelligence comes in. I think there's huge possibilities now to use artificial intelligence to do some of the processing in these devices. And then the question is, how far do you go? Because you could use artificial intelligence algorithms in these devices to make informed choices about how to process the data and turn those signals into actions. But for example, I saw an amazing documentary just recently about a scientist in the UK who was diagnosed with motor neuron disease. And so he had enough time. He knew how long he had before his disease would make him so debilitated that he wouldn't be able to do much more about the solution. So he had enough time to look at what technology was available at the absolute cutting edge and try and build devices, including his wheelchair and wearable devices that could make his life as comfortable and as normal as possible. And one of the things he looked at was how can I achieve speech? And so you're probably well aware of Stephen Hawking having motor neuron disease, and he has this computer that can turn his typed words into a sort of computer voice, but the typed words are done by his vision. So he uses his eyes to select words and put sentences together, and the voice sounds quite robotic. Well, this fellow, the technology has moved on a lot since then. And he was able to use artificial intelligence to reproduce almost exactly his own voice. So it sounds very, very natural. It sounds like he's really talking. But then he came to a critical decision where he could use the same technology as Stephen Hawking and use his eyes to select words and put a sentence together. But that's incredibly slow and cumbersome. Alternatively, he could use artificial intelligence to make an informed guess about what this guy would probably say if he was asked a certain question. So then you start to have the situation where the computer is actually taking over a little bit, and it's no longer him conversing and answering questions. It's really an algorithm, and so it starts to get a little bit into cyborg territory. So that's a very, very contentious area, but I think it's a fascinating area, and I think physics can make a huge impact on people with these sorts of really manifest physical disabilities in the future. And the other area related to that is nano robots. I mean, you can also imagine that as these devices get smaller, and people are already working on this, you may have small devices that can actually be injected into the vein, go through the bloodstream, go to a particular part of the body that they're targeted towards. And you could communicate with these devices externally. You could tell the device to release a drug to treat a tumor, for example. These things are coming, and in some cases they'll be contentious, but I think they have the potential to make really huge impacts.
Yeah, that all of those things sound incredibly interesting, and I'm excited to hear about them more, I guess.
Well, it'll be your generation that will develop them, and it'll be amazing to see what happens, I think, in the next 20 or 30 years.
Yeah, I think so too. So, final question. Do you have any final pearls or pitfalls to offer high school students that have an aptitude for physics?
Oh, look, I think my number one tip would be just find what really excites you and interests you. So if you have sort of a broad interest in physics, if you're really excited about physics, then the next step is to find the branch of physics that really excites you the most. That could be a particular branch of physics or the application of that area of physics. And once you find that, then you can really build a career out of it, and you get to spend the rest of your career doing something that you really, really enjoy, something that excites you every day, and work with some amazing people. So I think that would be my number one tip. And you don't necessarily have to find that straight away either. Sometimes it can take a while. You might need to try a few different branches of physics, or you know, you can even do voluntary work during your studies in different labs, in different fields, and get an idea of what people are doing before you make any decision. And even later on, even once you've completed your physics studies, even after you've done your PhD, you can still look at different ways, different directions you can go in. So you don't have to lock yourself in too early. But I think the sooner you can find the area that really excites you the most, that's when you can do great things. In terms of pitfalls, I guess maybe I've had people through my life, going right back to high school, and also in my work career, that fall into two categories, if you like. People who I would say have really inspired me and acted as role models for me. And then there's others that are, I would say, been much more negative voices. And I'm particularly when I go back to my high school years, I actually had science teachers who told me I would never do anything useful with my life. But to be fair, I was a bit of a class clown when I was at high school, and I wasn't very focused. So I did goof off a fair bit. But yeah, I actually had science teachers who told me that I wouldn't amount to anything. But then, and partly, to be honest, that was part of the reason I didn't go to university after I left high school, because I had a lot of doubts about my own abilities and what I could do with my career. And it wasn't until I was a little older and a little more mature that I started to develop a bit more self-belief, I guess. And that's when where the positive influences come in, meeting people who you can see as role models because they're doing things that excite you and they're doing great work. And I've had several of those all through my career. And I have to say, the ones that have been the most positive influences on my career, I still work with. Some of them I met, 40 years ago now, or more than 30 years ago. And they're the people that I'm still collaborating with and working with almost every day. So I think that's the key. Finding the area that really excites you and people that can motivate you.
Oh yeah, I agree with that. So thank you so much for such a rich insight into the world of medical physics, and I really appreciate the time you take that you're taking to inspire the next generation of physicists. And I'm sure that those that listen will share my appreciation. So thanks very much.
Oh, you're very welcome, Hugo. It was a pleasure, and I enjoyed chatting with you. So good luck with your series of interviews. I think they will be a really rich resource for the next generation of students coming through.
Yeah, hopefully that's the goal. Yeah. Well,
Terrific.